Okay, consider problem 63 from page 471 of your textbook. Problem 63 has a rational expression 3 over x squared minus 4x minus 5 minus 2 over x squared minus 6x plus 5, where 2 over x squared minus 6x plus 5 is also a rational expression. And we're supposed to subtract these rational expressions from one another. If you recall from Tuesday's class, all we have to do is we are going to take both of our denominators. In this instance, the denominator of the first rational expression is going to be x squared minus 4x minus 5. And the denominator of the second rational expression is going to be x squared minus 6x minus 5, or rather plus 5. And all we're going to do is we're going to figure out what the factors of these two rational expressions happen to be. Note that for x squared minus 4x minus 5, you may determine the factors using guess and check. You're going to find the factors of -5 or the last term. In this instance, 1 and 5 will multiply to be 5 because 5 is itself a prime number. And what we've got to do is we've got to figure out how we might add to be the middle term, -4. And you're going to ask yourself, is it the case that -1 plus 5 equals -4? And no, that doesn't work because -1 plus 5 gives you just 4, not -4. So then you're going to check to see if -5 and 1 added together gives you -4. And of course, you would be able to determine that, yes, indeed, -5 plus 1 gives you -4. And what we may learn from this is that the factors of x squared minus 4x minus 5 is going to be x minus 5 times x plus 1. Excellent. And we also have to do the same thing for the second trinomial here. We're going to use guess and check as well. But in this instance, I need the factors, two factors of 5, which add to -6, which at first seems a little bit tricky. But consider that 5 plus 1, of course, equals a +6. And if you remember that a -5 times a -1 will indeed give you a +5, then I hope that you can see that -5 minus 1 will indeed add up to -6. So from this, we learn that x minus 5 and x minus 6 is indeed, or are indeed, the factors of the second rational expression. So now we have 3 over x minus 5 times x plus 1. And this is minus 2 over x minus 5 times x minus 6. Excellent. Let's make sure you don't get your factors backwards by some strange reason. Now, what we're going to do with these prime factors of our denominator is we are actually going to calculate the LCD or the LCM between the two rational expressions. And how we do that is by selecting out our common term. And in this instance, our common term is x minus 5. And then we will look at the terms that we don't have in common. We don't have an x minus 6, and we don't have an x plus 1 in common. And so x minus 5 times x plus 1 times x minus 6 is the goal. This is the goal for how we want to finesse the two rational expressions that we are, subtracting one from the other from. So what this is going to tell us is that if you look at your first rational expression over here, we have 3 divided by x minus 5 times x plus 1. Well, we have an x minus 5 term, and we have an x plus 1 term. So what don't we have? We don't have that x minus 6 term, or the prime factor that exists in the prime factorization tree below. So if we're looking at this x squared minus 4x minus 5 term, you'll see that its prime factors are x minus 5 plus x plus 1. And the only prime factor that it's missing is that x minus 1 term, or x minus 6 term, rather, that exists in the row below. So you either look at your goal in order to determine what's missing from your 3 over x minus 5 times x plus 1, or you're going to look to the prime factorization tree on the row either above or below whatever factors you're looking at. So in this instance, what this tells me is I've got an x minus 5 times x plus 1 for this first fraction, and I will multiply the first fraction by the missing factor, x minus 6 over x minus 6. And I'm going to do the same thing for my second fraction. I've got 2 over x minus 5 times x minus 6. I will multiply it by its missing factor, which happens to be x plus 1. So now we've got a new problem statement. We've got 3 times x minus 6 minus 2 times x plus 1. All of this will be over x minus 5 times x plus 1 times x minus 6. Go ahead and use distribution. You'll get 3 times x plus 3 times negative 6 plus negative 2 times x plus negative 2 times 1 all over x minus 5 times x plus 1 times x minus 6. Take a deep breath. You're going to do 3 times x or 3x. You'll have positive and a negative is a negative. 3 times 6 gives you 18. Positive and negative is a negative. 2 times x is 2x. Positive and negative is a negative. 2 times 1 is 2. So we'll have all of that over x minus 5 times x plus 1 times x minus 6. Voila. Okay, so now we can go ahead and do some rearrangement on the terms that were given. So I'm going to go ahead and move my negative 2x forward in the stack, and I'll have my negative 18 minus 2 over there. Okay, and you'll note that 18 minus 2, if I owe you $18 and then I owe you $2 more, I should owe you $20 total. I have 3x minus 2x. That's going to give me a 1x. So I have 1x minus 20 all over x minus 5 times x plus 1 times x minus 6. So, or we just have x minus 20 all over blah, 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 blah. So we have x minus 5 times x plus 1 times x minus 6. And unfortunately, that's pretty much all we can do because x minus 20, this factor here, is already a prime factor, meaning it's already a prime polynomial. So you're not going to find any prime polynomial that will divide x minus 20 apart from itself in 1. So that is all we can do right now. All right. That is pretty much all there is to problem 63. Moving along, we'll now look at problem 72. Most of these problems are going to be fairly similar to one another. So once you get the hang of just using factoring and you understand how to calculate that LCM, LCD value, you're going to do the same thing for all of these problems for the most part. We're going to go to the side of our page and calculate the LCM for our two denominators. In this instance, we got to use guess and check to find the factors of 15. You'll note that 5 and 3, of course, gives you 15. And if I make one of these negative, 5 minus 3 does indeed give me a positive 2. So what that tells me is I'll have x plus 5 times x minus 3 as one of my factors for x squared plus 2x minus 15. And I'm going to do the same thing for x squared minus x minus 6. I'm going to do prime factorization on a negative 6. And what I'm looking for is something that will add to negative 1. You'll note that negative 1 and positive 6, if I do this, I'll get, and I add these together, I will get a positive 5, which of course is not what we want. But if I do a negative 6 and say a positive 1, that will indeed give me that negative 5 value that I'm looking for. So this tells me that my factors must be x minus 6 and x plus 1. So, okay, so we've got 4 all over x plus 5 times x minus 3. And this is added with 3 all over x minus 6 times x plus 1. All right. Now we're going to try to calculate the LCM so that we can find a common denominator because you cannot add these fractions without a common denominator. So the entire purpose of calculating this LCM slash LCD is to get these two fractions to have a common term. So to do that, calculating the LCM, we will select out the terms that we have in common. And what you'll see is that in these polynomials, there are in fact no prime polynomials that are in common between x squared plus 2x minus 15 and x squared minus x minus 6, which is a shame. So what this is telling us is that our goal is simply x plus 5 times x minus 3, x minus 6, and x plus 1, which is kind of a bummer. Because really what that says it looks like I've drawn on the screen somehow. Not sure how I did that with Zoom. That was a boomer moment on my part. Sorry, guys. Backtracking a little bit. I kind of messed up my screen. Should have had x plus 5 times x minus 3 times x minus 6 times x plus 1. Okay, so because there are no terms in common, you're just going to, of course, write out all of the prime polynomials that you don't have in common. In this instance, what we arrive at is kind of a shame because what it means to say to us is that calculating the LCM was more or less a waste of time. So you've got this 4 over x plus 5 times x minus 3. And all our LCM really told us to do was to multiply by the opposing base, essentially, because our opposing base was already this x minus 6 times x plus 1. So, you know, sometimes that's the case. So we're going to multiply the opposing base by this term 4, and we're going to add it with 3 over x minus 6 times x plus 1. That will be multiplied by its opposing base, which happens to be x plus 5 times x minus 3. Now, this is going to look like one heckin' mess, but what we can do is we can do some shortcuts. We know that the denominator, for example, is going to be the same. So we're going to have this x plus 5 times x minus 3 times x minus 6 times x plus 1. That will all be in our denominator. That much we know for sure. And then this 4 times x minus 6 times x plus 1, we can do something with that. But for now, I'm just going to, for the sake of accounting, go ahead and write it down just like that. Now, what we're going to do with this x minus 6 times x plus 1 is we're going to note that x minus 6 times x plus 1 is actually equal to x squared minus x minus 6. So I could have just written x squared minus x minus 6 in my numerator, and vice versa. This x plus 5 times x minus 3, of course, that's equal to x squared plus 2x minus 15. So I'm going to go ahead and just write that in here. And all of this will be divided by x plus 5 times x minus 3 times x minus 6 times x plus 1. Oh my goodness. So at this point in time, just take a deep breath. You're going to distribute your 4. So you'll have a 4x squared minus 4x. And positive 4 times a negative 6 is going to be a negative 4 times 6. Well, 6, 12, 18, 24. We're going to distribute this 3 to all of our terms. So we'll have a 3x squared. 3 times 2 is 6. Positive and negative is a negative. 3 times 15 is what? Well, 15 times 2 is 30. 15 times 3 should give me 45 if my mental math is working today. So all of this will be over x plus 3 times x minus 3 times x minus 6 times x plus 1. Awesome. And we're just going to go ahead and use that commutative law, group our like terms. And go from there. You'll note that 4x squared may be added with 3x squared. So by the commutative law and by grouping like terms, I may go ahead and add my 4 with my 3, giving me 7x squared. Now I'm going to do the same thing for all of these terms. I got a negative 4x here. I've got a positive 6x. Well, if I have $6 in my bank account, but I take $4 out, I'm going to have $2 left in my bank account. And if I've got $45 in debt that I owe you, and I owe you at a later point in time 24 more dollars, well, 45 plus 24 should give me 69. So I'll be in debt to you $69. And this will be all over x plus 5 times x minus 3 times x minus 6 times x plus 1. Make sure that everything is all underneath your denominator. Or I'm sorry, all underneath the vertical line, rather. Okay, so at this point in time, you are kind of stuck because we either have to say this is as good as we can do, or we may try to use some polynomial division, or we may try to factor this numerator expression. So either way, you're going to be essentially out the same amount of time. If you are somebody who would like to try using polynomial division, you're just going to write your term, one of your terms that exists in the denominator, say this x plus 1, and you're going to see if it will divide evenly into 7x squared plus 2x plus 69. So how this works, if you recall from Math 950, is you're actually going to look to this x term, and with the x term, you're going to try to guess how many times x will go into 7x squared. And said another way, you're going to try to guess what you can multiply with your x term such that it gives you 7x squared. And of course, I hope everybody guessed, well, if I just take a 7x and I multiply it with x, I'm going to get that 7x squared term. So we will, of course, say that x will go into 7x squared 7x times. Now, here's what you do with this information. You are going to back multiply just like with your ordinary division algorithm. So you'll have 7x times x, which gives you 7x squared, and 7x times 1, which gives you 7x. And you subtract. You'll note that your x squared terms cancel out. So you get 0 plus 2x minus 7x. Well, 2 minus 7 gives me negative 5. I have an x, and I can, of course, drop down my 69, just like dropping down the digits that are left over in ordinary division. Now we're going to ask ourselves, how many times does x go into negative 5x? So I'm going to ask myself, x times blank gives me negative 5x, and everybody should have responded on negative 5. So then you get negative 5, and you're going to back multiply. So you'd have negative 5 times x, which gives you negative 5x, and a negative 5 times 1, which is just negative 5. And of course, you're going to subtract this from everything above. So subtraction causes the signs to change. So your negative 5x becomes a positive 5x, and your negative 5 over here becomes a positive 5. And so what that means is that when you add everything together, your x terms will, of course, cancel out, but you are unfortunately left with some remaining digits. In this instance, you have 69 plus 5, which gives you, 74, which would be your remainder. And what this tells you is this means that x plus 1 does not divide your numerator, which in this instance is 7x squared plus 2x plus 69. So, yeah, that's a little bit of a disappointment, to say the least. It was very, very close, but unfortunately no cigar. So again, students can use polynomial division, and if you're really, really careful, you can basically check through each one of these factors to see whether or not the factors themselves are able to divide whatever exists in your numerator. An alternative approach to doing that would be to focus in on your numerator and say, take 69, multiply it with 7, which 7 times 9 is 63, carry your 6. 7 times 6 is 42, plus 6 gives you 48. So I should have 483. Now the challenge is, what are the factors of 483 that will add to be, in this instance, 2? And so if you remember factor by grouping, you take the last term and the first term, you multiply those together. In this instance, you're going to get 69. And we definitely need to double check our math just to make sure that we are indeed going to get 69. But it does look like we've done everything correctly. And so at this point, we want to know the factors of 483 such that they add to 2. So there is going to be something here which allows us to add to 2, probably something pretty big. So I'm going to go ahead. I'm going to say at this moment in time, what the factors of 483 are. And the computer says that we have, for 483, we can find the factors of being 3, 7, 21, 23, 69, 161, and 483, which makes sense. And so if you note, two of our factors would be this 21 and 23. And if I make one positive and one negative, I should be able to hit that 2. So let me go ahead. I'm going to make, suppose I have a positive 23 and add it with a negative 21. That will indeed give me 2 at the end of the day when I add those together. So what this tells me is, this tells me that the 7x squared plus 2x plus 69, what do we say, 7x squared plus 2x plus 69 must equal 7x squared plus 21x minus, I'm sorry, whoops, I got that backwards, plus 23x rather, 23x minus 21x plus 69. Okay. Now I'm probably going to have to do one of the negative sign switcheroo tactics, but we'll cross that bridge when we get there. For now, however, let's see, do we have anything that we can work with? This 23 is a little bit troubling. Don't like the 23 there. Is 23 a factor of 69? Let's go ahead and check. 23 times 3. 3 times 3 is 9. 3 times 2 gives you 6. So I actually need to do a little bit of rearrangement here, guys. I'm going to rearrange my terms real quick. I'm going to switch the order. My 21, I'm going to move it forward, and I'll back my 23x next to the 69, because that way I'll have my factors straight. So at any rate, what I just found was that 23 is in fact a factor of 69, and which is great because it means that we can pull out a 23 from 23x plus 69, and that leaves us x plus 3. Awesome. So our goal here would be to turn this thing into an x plus 3 situation as well. Whether that will happen or not, I don't know. We'll see. So we can definitely pull out a 7 and an x, and that would leave us an x minus 3. But unfortunately, that's not really what I want, because we really need both of these factors to be the same thing. And so we're going to have to go back to the drawing board here somewhere. What can we do? What can we do? Well, gang, this probably tells us, and I don't like to say this, but this probably tells us that we might be dealing with a situation where there are complex solutions. That's one option, one possibility. Or the second possibility is that we have what is known as a prime polynomial, which means that even if you could factor the polynomial, the solutions themselves are going to be really, really nasty looking. And so pretty much, even though this factor by grouping should have worked, the reason why it is in fact not working, or it's not yielding the correct setup by which you can then do some rearrangement and find some nice factors, is because the actual solutions to this polynomial must either be complex, or it's also possible that you've got what we're really dealing with when we talk about 7x squared plus 2x plus 69 is we've got a prime polynomial. And so again, my apologies. It is good to view a situation where the factor by grouping algorithm fails. I went through the math and I double checked the math, and it doesn't seem like the math is incorrect. So our factor by grouping should have worked. But the reason why it's not working is because this polynomial is in fact going to be a little bit more complicated. It's going to have complex solutions, or it will be a prime polynomial. Now, one of the ways that you could double check yourself in your own time would be to go ahead and try by polynomial division. You would try seeing if you could divide x minus 6 into 7x squared plus 2x plus 69. You would then try to see whether you could divide x minus 3 into 7x squared plus 2x plus 69. And you would see if you could find whether or not x plus 5 would divide 7x squared plus 2x plus 69 using the methodology described here. And what you should find, if my math is correct, is that for each one of these polynomials, you're actually not going to be able to divide the factors into 7x squared plus 2x plus 69. And so this is, in fact, our solution. So it cannot be simplified. And unfortunately, that is sometimes the case. Sometimes you spend 20 minutes trying to simplify a problem statement only to realize that you are, in fact, dealing with some nasty scenario where you don't have a way to simplify the polynomial. Now, I will, on our exam, try to make sure that the example that I give you on the exam isn't going to be something as nasty as this. But again, no guarantees. All right, and that brings us to today's lesson, which is about complex rational expressions. And a complex rational expression is kind of nasty, okay? In your lower level math classes, in Math 900, one of the reasons why the Romans preferred to use what are known as mixed numbers for being able to divide and or add, subtract, and do all of these various other calculations is because whenever you have a situation where maybe you're adding, say, fractions and then taking those fractions and dividing it with some other sequence of fractions that may also be added with each other, this situation divided by this situation down here just looks like utter nonsense. But in fact, this is what is known as a complex rational expression. Okay? So this is, in fact, a complex rational expression. And the way that a Roman, of course, would have approached it is by trying to figure out what 1/3 plus 1/2 happened to be. They would try to determine, like, what is this exactly? And of course, you could do this in a number of different ways. One method would be to multiply by the opposing base. 1/3 times 2/2 would be 2/6. And 1/2 times 3/3 would be 3/6. And of course, when you add these two fractions together, you get 6 in your denominator. 2 plus 3 gives you 5. So all of this nonsense in our numerator simplifies to 5/6. And then similarly, if we break off the denominator and we just try to examine the fractions in our denominator, we're going to add 1/5 with 1/7. And you could, say, multiply by the opposing base. And from there, you would get 7/35 plus 5/35, which would be 7 plus 5 gives you 12. And that would be all over 35. So we have 12 over 35 in our denominator. And whenever you're dividing a fraction with a fraction, just you flip and multiply your fractions together. So you'd have 5 times 35 and 6 times 12. Don't be afraid of doing the multiplication algorithm. 5 times 5 is 25. Here are your 2. 5 times 3 is 15. Plus 2 gives you 17. So we get 175 in our numerator. And we have 12 times 6, which should be, what is that, 72, I believe. But if we did not know our multiplication tables, 6 times 2 gives you 12. Carry your 1. 6 times 1 is 6, plus 1 gives you 7. So you do indeed have 72 in your denominator. And of course, this is your answer, which looks a lot prettier as a mixed number. Now, what we're going to learn about in chapter 7.6 is that we may use a very similar process or strategy in order to figure out what, say, 3 divided by 4x minus x over 3 happens to be. What is this actually equal to? Or perhaps you have a situation like x plus 1 over x plus 4 minus 1 all over 16. What would this be equal to? And to be honest with you, these are really nasty situations. So if you were stranded on a desert island, you really wouldn't want to be confronted with these rather dire looking rational expressions. But if you were, then I am here to help you because we are going to figure this out together. So using the Roman strategy of just attacking the numerator or the denominator, this is perfectly adequate for being able to address any of these rational expression problems. Sometimes, however, it's just a little bit trickier to determine what exactly is going to be your common denominator in some cases. But if we, for example, try to look at this first problem, 3 over 4 over x minus x over 3, and we just look at its denominator, which happens to be the 4 over x minus x over 3, and we try to figure out what is this denominator going to be equal to. We know that we could use the LCM method to try to find a common denominator. And in this instance, it's going to be really easy because for my x, I just have an x term. For my 3, I just have a 3 term. So my LCM slash LCD is going to just be x times 3 because we don't have any terms in common. So we're just writing the terms that we do have. And what this tells you is you could take what you don't have in the denominator of 4 over x. In this instance, we're missing a 3. And we're going to multiply 4 over x by 3 over 3. And we're going to do the same thing for x over 3. We're going to take what we don't have, which would be this x term. I'm going to multiply in the top and the bottom of the fraction by x over x. And so now we've got 4 times 3 gives us 12. 3 times x gives us 3x. We have a 3x in our other denominator, and x times x gives us x squared. So finally, we will be left with 12 minus x squared all over 3x, and that is our answer. Sort of. We may have to, at that point in time, figure out if you can finesse this answer a little bit. But for now, I believe that's all we can do because while a 3 will indeed divide a 12, 3 will not divide 1. Well, x will divide x squared. X will not divide the 12. Okay, so now let's look at this second example problem, this x plus 1 over x plus 4 minus 1 all over 16. Let's go ahead. We're going to write it out. We've got x plus 1 all over x plus 4 minus 1 all over 16. Just double check to make sure we got all those signs correct. Brilliant. Okay, so now we're going to examine the numerator of our expression, since that's where we've got all of these complex rational terms. And we're going to just write out x plus 1 over x plus 4 minus 1. And what we're going to try to do is we're going to try to figure out how can I add x plus 1 with x plus 1 over x plus 4 with the 1 term. And it's going to be a little bit tricky. Note that -1 is the same thing as negative 1 over 1. So you could, of course, try to change 1 into a rational number. So you should have 1 over 1. And then if you guys remember, the LCM of 1 and some number is just that number. So in this instance, we have the LCM of 1 and x plus 4. So that would just be x plus 4. And what that tells me is I need to multiply this second fraction by x plus 4 over x plus 4. And I'm going to have x plus 1 over x plus 4. For my first fraction, 1 times x plus 4 just gives me x plus 4 on top. 1 times x plus 4 just gives me x plus 4 on bottom. And we can go ahead and combine our denominators together since we have a common denominator. And all you've got is you've got x plus 1 minus, here's the trick, guys, watch out, minus the whole chunk, x plus 4. If you do not have parentheses around your x plus 4, you are just wrong because you are subtracting off the whole entire chunk. So now we've got x plus 1. Once you distribute your negative symbol, you'll get a negative x minus 4 all over x plus 4. And you're going to use the commutative law to combine your like terms. You'll realize that x minus x gives you 0. 1 minus 4 gives you a negative 3. So you have a negative 3 all over x plus 4. And that is your answer. Okay. Now, sometimes finding an LCM is actually going to be probably, and I should back up, finding an LCM and then adding or subtracting your fractions in the numerator and or the denominator is actually going to be a longer process than what you really need to do in order to solve some of these complex rational expressions. And so while the LCM method does exist and is in fact perfectly adequate for being able to attack many of these different problem statements, what you'll see is that if you have some expressions such as 5 over t minus 3 over t cubed all over, let's say this is 10 over t plus 3 over t squared. Say we've got a situation like this, and we're asking ourselves, hey, what is this equal to? While it's certainly true that you could go to the side of your paper and find, say, the LCM of the numerator and the LCM of the denominator and try to add your fractions together or subtract your fractions from one another, there is, in fact, a better way. What we're going to do instead of all of that mess is we're going to try to simplify our fractions all in one go. So this is going to be a little bit of a weird technique, and some students may understand it. Other students might not figure it out or might not understand it, and that's totally okay. But if you look at the LCM of just the terms in your denominator, so you've got a t here, a t cubed here, and a t squared here, you'll see that for t, well, that's just t. For t squared, you've got a t times t. For t cubed, you've got a t times t times t. And so if you calculated your LCM or your LCD, what you'll find is we've got a t in common, and we've got some t's left over. So our LCM slash LCD is in fact going to be just the biggest factor here, or the t cubed. So what we're going to do with this information is that we're not going to try to add all of our fractions together, but instead we will make a simplification by multiplying the numerator and the denominator of our expression very carefully by a very special term. We will multiply the numerator and the denominator by the LCM over itself. And what this is going to do is this is going to mean that we got to use distribution on the numerator with t cubed And we're going to do the same thing in our denominator. We would have t cubed times 10 over t plus 3 over t squared. And this is going to be kind of an extension of what was known as the Hindu Arabic method, which we talked about in our Math 950s course, which is a method for simplifying and or solving linear equations by first essentially removing all fractions inside of the linear equation by multiplying both sides of a specific equation by the LCM of whatever were in the denominators. And by doing this, you are able to then clear the fractions. So what we're doing now is we're multiplying the top and the bottom of our first fraction by this t cubed over t cubed, which at this point in time, while it might seem unnecessary, it's certainly not an illegal move because t cubed divided by itself is just going to be 1. So we've cleverly disguised 1 here as t cubed over t cubed. But what's going to happen here is where the magic begins, because you will have t cubed times 5 over t minus t cubed times 3 over t cubed, and t cubed will cancel out with t cubed. Your t cubed will in fact divide with t, and you'll be left with a t squared. Same thing will happen in your denominator. You'll have a t cubed times 10 over t plus a t cubed times 3 over t squared. And your t will also divide out with the t cubed. You'll be left with a t squared. Your t squared will divide out. You'll be left with a t. So all in all, if we're really, really careful about doing this, we should have a t squared times 5 minus 3 all over t squared times 10 minus t times 3. So said another way, we've got 5t squared minus 3 on top, all over 10t squared minus 3t on bottom. At this point, the only thing that you have to double check is to see if whether or not your numerator and or your denominator may be simplified. You want to check to see whether you can factor out a GCF, which you can't in this instance because the factors of 5 don't divide 3 and vice versa, and the factors of 3 don't divide 10 and vice versa. So this is pretty much as good as we can do for right now. And that's all there is to this method. I hope you can see that by multiplying the top and the bottom of your denominator by t cubed, all we had to keep track of was the fact that we were doing distribution. And then once you simplify your distribution, which can be done in a single step, if you skip over, if you're comfortable with your mental math, you can definitely do it in a single step. And what that'll allow you to do is that'll allow you to just write 5t squared minus 3 all over 10t squared minus 3t. So it is a much nicer way of being able to simplify everything. Now, let's do one last example. Suppose you have a complex rational expression, -6 all over y squared plus 5y plus 6. And this is divided by 2 over y plus 3 minus 3 over y plus 2. And the question is, what is this behemoth equal to? All right, so if we're going to use the LCM technique, multiplying the numerator or the denominator by the LCM rather, what we're going to have to do is we're going to have to figure out what the factors of this y squared plus 5y plus 6 happen to be. And in general, for these problems in the section, whenever you see that you've got a trinomial expression, go ahead and factor that if you can, because usually when you factor it, that's going to give you a key as to the next step of the process. So in this instance, when we find the factors of y squared plus 5y plus 6, you'll see that by guess and check, the factors of 6 are 2 and 3. 2 plus 3 adds to 5, and that tells you that you've got a factor of y plus 2 and y plus 3. So you may say that this is the same thing as -6 all over y plus 2 times y plus 3 divided by, and we've got a 2 over y plus 3 minus 3 over y plus 2. Okay, take a deep breath. Take a deep breath. And I'm saying that mostly for myself. All right, so now we're going to calculate the LCM of every single one of our denominators. So we're going to calculate the LCM of y plus 3 and y plus 2, as well as y plus 2 times y plus 3. And I hope that you guys can see with your own eyes the LCM of this is going to just be y plus 2 times y plus 3. But if you need to go through the LCM calculation, go ahead and do so on paper and double check and verify that it will in fact be this y plus 2 times y plus 3. So without further ado, go ahead, you're going to multiply your numerator and your denominator of your expression by y plus 2 times y plus 3. And so what will happen in the numerator is everything here will cancel out. You'll be left with a big fat -6. What will happen in your denominator is you're going to have 2 over y plus 3. That will be multiplied with y plus 2 times y plus 3. And voila, your y plus 3 starts canceling out. You will have a 3 over y plus 2 times y plus 2 times y plus 3. And your y plus 2 cancels out there again. And so at the end of the day, you got -6 over 2 times y plus 2 minus 3 times y plus 3. And that's it. Done. For the most part. Now, we do in fact have to simplify this denominator. Note that while I'm basically done, and if you had gotten to this point, you would have received most of the credit, you can in fact do that distribution law. Go ahead and distribute. You're going to have 2 times y plus 2 times 2 is 4. -3 times y is -3y, and a -3 times a +3, which just gives me a -9. Okay, so doing some rearrangement, we get some -6 all over 2y minus 3y, which is a -y, minus 5. And we can do a little bit better than that. We can, in fact, factor out a -1 in your numerator and a -1 in your denominator. You'll be left with a 6 over y plus 5, which is, in fact, the best answer. Okay. Of course, I recommend students go ahead and look at the problems in their homework that are related to this particular section and just make sure that you've got everything under control. Of course, there are plenty of examples in the chapter itself, and I recommend students go through all of the example problems if they're really, really struggling with this particular concept of being able to use the LCM to negate or cancel and or simplify the terms in your numerator and or denominator. Another thing I recommend students doing is to try practicing with the concepts that we learn in class on a very basic example. So like when I was first trying to figure out all of the different ways that you could manipulate complex rational expression, I would often go back to just adding some very basic fractions with one another in our numerator and our denominator. So if I was trying to figure out like, why does that LCM technique of multiplying on the numerator and denominator work? I might try figuring out how it works for this particular example. And of course, I would calculate the LCM of 2, 3, 4, and 5. And I would find that that would be close to 20, if not 20. So I would take the number 20, I'd multiply it on top and on the bottom, and I'd see, what happens when I multiply 20 across these terms here, and I multiply 20 across 1/4 plus 1/5. And for me, that really helps me kind of wrap my mind around the level of abstraction that is introduced whenever you have the variables in your fraction itself. And then in addition to this, we're also kind of exploiting some of the properties of being able to multiply your numerator and denominator in like part with whatever you want to multiply those numbers with. But I hope you guys will see by giving yourselves a couple of practice problems, going through some of the exercises in your textbook, as well as maybe playing around with the numbers yourself, that in fact, this LCM technique is legitimate. You can go break out a calculator and you will get the same if you take your numerator and divide it by your denominator, you will get the same answer as you do whenever you multiply through and you clear your denominator out, and then you perform the division operation at that point in time. All right, so now transitioning, we're now in section 7.7. So in section 7.7, you are actually asked to solve equations, find the solution equations, which have or contain rational expressions. Okay, so you're asked to solve equations that have rational expressions. I'm just going to give you guys an example. Suppose you've got 4 over x plus 1, and that's equal to 3 over x plus 1 plus 5. Okay. Say we want to solve this particular equation. There are a couple of things that we have to know as students. First of all, what does solve for an equation mean? It means that we're going to do rearrangement on our terms to get x by itself and everything on either one side of the equal sign or the other side of the equal sign. But another thing that it means is that when you have x equal to something, that something that x is equal to actually has to make sense. And there is, in fact, a problem whenever we're dealing with these rational expressions. And that is simply not all values of x are legitimate. So the first thing we have to do whenever we're solving equations with rational expression is we have to figure out what points exist such that x becomes, or solution rather, becomes absolute nonsense. And you'll recall from maybe your middle school, maybe your elementary school program, we said that if you have a number and you divide it by 0, this is nonsense. So what we're going to do is we're going to set the denominators of the rational expressions inside of our equation not equal to 0, because those are points where x can not equal some value, because if it did, then you would be dividing by 0. So for example, you have this rational expression 4 divided by x plus 1. What we're going to do is we're going to take the denominator x plus 1. We're going to say that this cannot equal 0, because if it equals 0, we would be in trouble. Now, using our subtraction on both sides is a kind of a shortcut. I'm going to subtract 1 on both sides. 1 minus 1 gives me 0, so I've got x plus 0. And I'm saying this cannot equal negative 1. X plus 0 is just x, so x cannot equal negative 1, because if it did, the rational expression 4 divided by x plus 1 would be nonsense. If we wanted to check to see if that was the case, you could, of course, plug in your negative 1 into your rational expression 4 over x plus 1, and you'd see that negative 1 plus 1 does indeed give us 0, which gives us utter nonsense if we were to manipulate this equation around. All right, so this is the first thing we have to do whenever we're approaching these rational expressions. We have to set our denominators not equal to 0 if you have an x value in your denominator. If you don't have your x value in your denominator, all you have to do is just finesse the equation to get your x equal to something, just like you would with a multi-step LUV problem statement. But in this instance, we found that x cannot equal negative 1, because if it did, then we would have a problem. And what this means ultimately is that if we were to solve this equation and we found that the solution was indeed that x must equal negative 1, then we would have a situation where there is in fact no solution, because x cannot create nonsense in the equation itself by being equal to negative 1 and simultaneously have a situation where negative 1 is in fact the only solution that exists in the equation. That would be just kind of nonsense. So, all right, with that out of the way, what we're going to do now is twofold. we are going to calculate an LCM of the rational expressions. And we will then use the LCM and we're going to multiply it across the entire expression so that we can cancel out our denominators. So what does that look like? Well, I'm going to calculate the LCM of x plus 1 and x plus 1, which I hope everybody would agree is just going to be x plus 1. But what happens if I take this x plus 1 and I multiply it across the entire equation? You're going to have 4 over x plus 1, and this will be multiplied by x plus 1. This would be equal to 3 over x plus 1 times x plus 1. And you're going to have a 5 times x plus 1. Remember, you got to use your distribution law here. So your x plus 1 needs to multiply through by everything in your equation. Now what's going to happen is your x plus 1's cancel out. So you just are left with a 4. And your x plus 1 over here cancels out. You're just left with a 3. And now you've got 5, which can distribute. So you get 5 times x, and 5 times 1 is just 5. Go ahead, manipulate your numbers around. 3 plus 5 gives you 8. You get 8 plus 5x is equal to 4. Subtract your 8 on both sides very carefully. You get 5x is equal to negative 8 minus 4, which gives you negative 4. And go ahead and divide off 5 on both sides. So now you get x is equal to negative 4/5. Voila. Voila. So the only trick that we need to know in this particular section is that by multiplying a equation through by the LCM, this is called the Hindu-Arabic method. What will happen is your LCM will cancel out. I'm sorry, the LCM that you've multiplied the equation through will cancel out with the denominator of the rational expressions. And so you'll be left with whatever exists in your numerator. And generally, you'll be left with an equation where there are no fractions. This can be, of course, used in any situation where you have fractional coefficients in front of your x. If you just want to, manipulate your equation such that you don't have any fraction coefficients. So this is a technique that will always, always, always work. All right. Suppose we have another example. Say we have 5 over x plus 3 plus 2 over x plus 2, and all of this is going to equal to 10. And we want to, solve for x. Our step 1 is we're going to just find our nonsense points. So we're going to take our denominators. We're going to set them not equal to 0, because if they were equal to 0, that would be an issue. So we've got an x plus 3, that can't equal 0, and an x plus 2, that can also not equal 0. We'll go ahead, we'll subtract 3 on both sides. We get x is not equal to negative 3. We get x is not equal to negative 2. Bam, bam, boom. You got some nice stuff there. Now, for step 2, we need to calculate the LCM of x plus 3 and x plus 2. Since both of these are prime polynomials, the LCM will in fact just be x plus 3 times x plus 2. What we will do with this information is we are going to multiply this entire equation, 5 over x plus 3 plus 2 over x plus 2 is equal to 10. We're going to multiply this entire thing by x plus 3 times x plus 2. Now, there are going to be a lot of students that want to skip this step, guys. There are going to be a lot of students that want to skip this step, and they are going to lose points. They're going to skip this step. They're not going to write things down. Things won't cancel properly, and they're going to just lose points on their examination. I am foretelling it like a fortune teller. I'm telling you guys, it's going to happen. Don't let that individual be you. Write it out. It's okay to do the math on the paper. That's what the paper is for. If we wanted to do the math instantaneously, we would in fact get the computer. And if we did the math on the paper, what we need to see is the numerator and the denominator actually canceling out with one another. We need to see x plus 3 canceling out with x plus 3, leaving us 5 times x plus 2. We should see the x plus 2 terms canceling out, leaving us with 2 times x plus 3. And then finally, on our other side of the equal sign, most critically, you need to make sure your 10 is being multiplied with x plus 3 times x plus 2. Okay. At this point, you're going to have to do some distribution. You'll get some 5x plus 10. 5 times x is 5x. 5 times 2 is 10. 2 times x is 2x. 2 times 3 is 6. This is all going to be equal to 10 times. Let's go ahead and we'll multiply this out together. You're going to get an x squared. 3x and a 2x should give us a 5x. 3 times 2 should give us 6. So you should have x plus 3 times x plus 2, and that will equal x squared plus 5x plus 6. Again, use FOIL method if you have to, or you can do extended division. I'm sorry, extended distribution. So you just do x times x plus 2 plus 3 times x plus 2. Go ahead and work out the math. This is what I'm doing in my head, by the way. It's going to give you the same thing, doesn't matter. All right, so now we're going to add our like terms with like terms after using the distribution law. 5x plus 2x gives us 7x. 10 plus 6 gives us 16. This is all equal to 10 times x squared, which gives 10x squared. 10 times 5x gives us 50x. And 10 times 6 is 60. We're going to go ahead and we'll subtract 16 on both sides now. We'll get 7x is equal to 10x squared plus 50x. And 60 minus 16, you're going to have to borrow a 10. 10 minus 6 gives you a 4. 5 minus 1 gives you 4. So you've got a positive 44. And go ahead and subtract off 7x on both sides. You get 0 is equal to 10x squared. 50 minus 70 is, of course, going to be 43 plus 44. Now, my bet would be that we cannot actually do this using the factoring by grouping method. But you could go to the side of your page. You'll do 44 times 10. That's going to give you 440. And then you would try to see whether or not the factors of 440 could indeed add to 43. You'd see that the factors of 440, if you were to factor this out, you're going to get 220, of course, 440 itself, 110, 88, 55, 44, 40, 20, 22, 10, 11, 8, 5, so on and so forth, 4 and 2 and 1, of course. So these are all the factors of 440. And you would have to basically select which one allows you to add to 43. Now, it does look like that, it does appear to be the case that 44 minus 1 would add to 43. So what that tells you is you could expand out this 10x squared to be 10x squared plus 44x minus x plus 44. And if we switch the order of our terms, we have 10x squared minus x plus 44x plus 44. Then if this is indeed factorable, we should be able to find some common terms. Of course, you would be able to take out, say, your x term here. You'd get 10x minus 1. But unfortunately, if you were to factor out 44, you get x plus 1. And so just like in our previous example, this is going to be one of those factor by grouping situations, which more or less demonstrates that you're going to be dealing with what is known as a complex solution, potentially, or possibly a what is known as a prime polynomial, which means that it can be factored and there will be real roots, but those roots will not be nice looking. And so in this instance, basically, as good as we can do up till this moment in time is just say that 0 will equal 10x squared plus 4x plus 44, and then just tell we can list that it has complex solutions or it is in fact a prime polynomial, which would mean that that while solutions do exist, the solutions are going to require us to use something like the quadratic equation in order to find out. The quadratic equation is not a difficult technique for students to learn about. Just as a side note, if you were so inclined to determine whether or not we would have complex roots in this case, if you recall from maybe your middle school or your high school mathematics, there was this thing they called the quadratic equation. They said that anytime you've got ax squared plus bx plus c equal to 0, i.e. the setup that we just had, this mess here, it's exactly the same situation, then x may be determined to be negative b plus minus the square root of b squared minus 4ac all over 2a. In this case, our b would be 43, our a will be 10, and our c is 44. So if you plug in your b to the b in this equation, you're going to see negative 43 plus minus the square root of 43 squared minus 4 times 10 times 44, which is going to be rather ridiculous, but I mean, it's possible that it's a real solution, all over 2 times a, which happens to be 10. So 2 times 10 gives you 20 in the denominator. You'll have negative 43 in your numerator, plus minus the square root of, we have to go to the side of our page, 43 times 43. 3 times 3 is 9. 3 times 4 gives you 12. Drop your 0. 4 times 3 is 12. 4 times 4 is 16. Plus 1 is 17. Add everything together. 9 and 0 is 9. 2 plus 2 is 4. 1 and 7 is 8. And you got a 1 left over. So you've got 1849. And I'm sorry, guys, but I don't think this is going to be smaller than 40 times 44. So we go to the side of our page. We'll do 44 times 40. Of course, you get a bunch of zeros, so you might as well just skip the first round. And you get 4 times 4 is 16. Carry your 1. 4 and 4 is 16. Plus 1 gives you 17. So you actually do have, you're going to have some real solutions, it would appear. So you've got negative 43 plus minus the square root of 1849 minus 1760. What I was about to say was, if 40 times 44 happened to be bigger than 1849, we would be essentially trying to take the square root of a negative number, because you'd have, something minus something else that is bigger than that something, which would give you a negative number. And then we would be trying to take a square root of the negative number, which would be a less than ideal situation. In this instance, we're taking the square root of a positive number, since 1849 minus 1760 will in fact be positive. So you do, you do the math here. 9 minus 0 is 9. Borrow a 10. 14 minus 6 should give you, that'll be 8. 7 minus 7 is 0. 1 minus 1 is 0. So you get the negative 43 plus minus the square root of 89 all over 20. That is what our x is equal to. Now, of course, students might say, well, I don't know how to calculate the square root of 89 by hand. Unfortunately, that's not the problem here. I mean, it is a problem naturally, because if you actually wanted to get a solution, you'd have to figure out what the square root of 89 was. But you could also, in this instance, simply leave that for someone else and say, this is my solution. Because even if you could take the square root of 89, that would be an approximation. So at the end of the day, if you want an exact solution, well, your exact solution is that you've got x is equal to negative 43 plus minus the square root of 89 all over 20. That is the exact solution. Once you start plugging numbers into a calculator, though, you're going to get an approximation. So you would have an approximate solution, but this, in fact, would be your solution to this equation. Of course, this is above the scope at this point in time. We will talk more about the quadratic equation. It's just something to introduce at this moment, because students might want to actually solve these problems, and it's not super difficult to do if you use the quadratic equation. But most of these problems are going to wind up being something that can actually simplify, and you'll get a nice looking clean answer. So one last problem, and I'll let you guys go. Suppose you've got a situation, say this is problem 73 in your textbook. Say you've got 5 over 2x minus 3, and this is equal to, now let me just check my battery. It's like my battery's getting a little low, but I think I should have enough to finish out this lesson. So we've got 5x over 2x minus 3. That's equal to 3x over x minus 1 minus 5 over 2x squared minus 5x plus 3. All right, so what we've learned in this class is that the first thing we're going to do is we're going to scan through our denominators. We're going to set each one of these denominators not equal to 0. So 2x minus 3 cannot equal 0. That means 2x cannot equal 3. And x cannot equal 3 halves as a solution. It also means x minus 1 cannot equal 0, or you add 1 on both sides, x cannot equal 1. It also means that we need to figure out what the factors of 2x squared minus 5x plus 3 happen to be. 3 times 2 gives you 6. So if you take 6 and find the factors, you'll see 6 and -6 and a +1 would add to -5. So we may expand out 2x squared minus 5x plus 3 using factor by grouping to 2x squared minus 6x plus x plus 3. And then we could take out you could take out a 2x and an x minus 3, and you just would be left with x plus 3, though. So that would be kind of a pain in the butt. So oh, what can we do? This should have worked, though. Should have been able to do this for this particular problem statement. It's a bummer that it didn't. Let me go ahead and I'm going to double check to see. Not sure why your textbook gave you one that had some nasty polynomial equations. Could be that we may need to switch our terms, switch the order of our terms around a little bit. Maybe instead you would try 2x squared minus plus x minus 6x plus 3. And then from here, you might try pulling out your x, so you'd get a 2x plus 1 here. And from this guy, you might pull out a 3, and you'd have a -2x plus 1. But the only problem is that pesky negative symbol, -5x plus 3. And it is, in fact, in your denominator for the number itself. Yeah, I'm just not exactly sure what I'm doing wrong when I'm factoring by grouping. So I'm going to have to look at this problem a little bit closer and, post a solution for what I'm doing here. Another method, however, which is a much more brute force way of doing things, would be to line up your terms and simply say, look, you have 2x squared minus 5x plus 3. So when you multiply these together, you've got to have your factors add to this -5. And what that means is that one of these factors, because the x terms will have to multiply to be 2, and 2 is a prime number, you can already guess that one of the factors must have a 2x and an x. But then also one of the factors must have a 3 and a 1. So you have a couple of different situations. Either it's going to be 2x plus 3 and an x minus 1. You might have a 2x minus 1 and x plus 3 type situation. You may have a 2x minus 3 and x plus 1. You may have a 2x plus 1 and an x minus 3, something like this. There's going to be a variety of different possibilities that you might have as factors. And once you essentially go through and use extended distribution on all of these different possibilities, what you will see is that the answer to this particular question will be that the factors of 2x squared minus 5x plus 3 are going to be 2x minus 3 and an x minus 1. So at some point, you would try 2x minus 3 and an x minus 1 as a possible factor. And what that means is you may, of course, because you've got 2x squared minus 5x plus 3, and this is not equal to 0, you may set 2x minus 3 times x minus 1. That won't equal 0. And what that essentially means for you is you've got x minus 1 does not equal 0. And of course, you can add 1 on both sides. And this more or less gives you the answer you had before, that x cannot equal 1, which is fine. That's not really that important. But then you've got the 2x minus 3, that can't equal 0. So you got plus 3, and 2x does not equal to 3. And you can divide by 2, or x doesn't equal to 3/2. And so I think maybe one of the reasons that the textbook did not factor this particular problem is they realized that it was simply what occurs after you were to, say, multiply everything through by 2x minus 3 and an x minus 1. So maybe they didn't even bother checking to see whether or not that was the case, or how easy it would be to, say, factor one of these particular terms. So whatever the case is, usually you don't get a problem statement this tricky. Usually you're gonna be able to actually get an answer before the universe freezes over. But whatever the case is, now we're going to take our equation. We've got 5 over 2x minus 3. We've got 3x over x minus 1 minus 5 over 2x squared minus 5x plus 3. And what we've done is we've kind of found the factors of that last term. We know the factors are going to be 2x minus 3 and x plus 1. I'm sorry, x minus 1. And so what this tells us is this says that the LCM of everything, the 2x minus 3 term, the x minus 1, and the 2x minus 3 times x minus 1 is going to be 2x minus 3 times x minus 1. And so you may go ahead and multiply everything through by 2x minus 3 and x minus 1. And when we do that, we are definitely going to clear our denominators. You're going to have 5 over 2x minus 3. This will be multiplied with 2x minus 3 times x minus 1. Here at 2x minus 3 terms will cancel. You'll have 5 times x minus 1 left over. That will be equal to 3x over x minus 1 multiplied with 2x minus 3 times x minus 1. Your x minus 1 terms will cancel out. You'll have a 3x times 2x minus 3 left over. And then finally, you've got 5 over 2x minus 3 times x minus 1. And all of this is multiplied with 2x minus 3 times x minus 1. So your 2x minus 3 terms cancel out, your x minus 1 terms cancel out, and you've got a 5 left over. So now you're just going to use your distribution. You got 5 times x is 5x, 5 times 1 is 5, 3x times 2x. Well, that 3 times 2 is 6. X times x is x squared. 3 times 3 is 9. X will be left over, minus 5. All right, now hopefully we're going to get some nice answers at some point in time. I will add 5 column-wise to both sides. That's going to cancel out. I'll go ahead and add 5x column-wise to both sides. You're going to get 0 is equal to 6x squared minus 4x. By the GCF technique, we can definitely factor out a 2x, and you'll have 2x times blah, blah, blah. In this instance, 2 times 3 gives you 6, and x times x gives you 6x. So 2x times 3x minus 2 times 2 is 4 should be equal to 0. So what is your solution? By the 0 law, it means we need to set our factors equal to 0. Of course, if we set 2x equal to 0, that means x must equal to 0 by the 0 law itself. And if we set 3x minus 2 equal to 0, and we add 2 on both sides, maybe in trouble here. Get, let's see, x will equal 2/3. Now, we're going to double check to make sure that we didn't violate any rules. We said that x could not equal 3/2, but what we actually have is we have x is equal to 2/3, so we should be okay. We also said that x could not equal 1. So since neither of the solutions that we have are part of our naughty list, these will in fact be our solutions that are allowed. Okay, guys. So this section is, of course, very, very long-winded, unfortunately, but sometimes that's the case. Sometimes you just get very, very long-winded answers. And, unfortunately, I don't know what else there is to say, but it is what it is. We're not always guaranteed to have some nice math at the end of the day. So when we do have nice math, it's always nice, obviously, but sometimes you're going to get some messes where you have to do some factor by grouping, and then just trying to figure out exactly how to line up your factor by grouping terms is going to be one of those more challenging situations, if you will. So, good luck on your homework. Send me a message if you have any questions. I'm not necessarily guaranteed to be able to answer your messages, but what I'll tell you is I will try my best to be online to answer my emails. If I'm on my emails and I see you've sent me a message, I will try my best to answer them. I'm not guaranteed to be able to answer them because I am going to be very, very busy in Rapid City, but this is a very challenging section, I realize, and so I'm here to help wherever I can, however I can, and I hope to be back after our fall break. Take care, guys.